Let's start with some basic complex numbers sums. The first one, the value of I squared. So as you all know, I is nothing but the square root of -1. Therefore, I can say that I squared is simply -1. Afterwards, 2I to the power of 2. Now I can extend this as so 2 to the power of 2 and I to the power of 2. 2 to the power of 2 becomes 4 and I becomes -1. So this becomes -4. -2 into I to the power of 2. I'm going to extend this as so -2 to the power of 2 becomes 4. I squared is -1 -4. I cube. Now I can break this into I into I squared. Now you know I squared is -1 into I becomes -I. I to the power of 4. I'm going to again break this into two components as so. I to the power of 2 is -1. -1 into -1 becomes +1. I to the power of 5. I'm going to break this into I to the power of 2 and I to the power of 3. I to the power of 2 becomes -1. And from the previous example, I to the power of 3 becomes -I. Together this becomes I. I to the power of 6. I to the power of 3 into I to the power of 3 becomes I to the power of 6. And from the previous example, you know, I to the power of 3 becomes is -I. So -I into -I becomes I squared. This again becomes -1 from here. Let's plot the following complex numbers. Now I have drawn the empty graph as follows. I have my real axis here and my imaginary axis here. So before plotting, I would like to examine the numbers that I have to determine the ranges. So I can see that by looking at these numbers, I'm gonna need 4 in each axis, in the positive side and the negative side. So first of all, I would like to separate the axis into 8 segments. So this is 1, 2, 3, 4, -1, -2, -3 and -4. In the imaginary plane, I have positive I, 2I, 3I, 4I. In the negative side of the imaginary axis, I have negative I, negative 2I, negative 3I, negative 4. I'm going to be using the color green to make it clear to you. So the first number that I have is 2I. So 2I is nothing but 0 plus 2I. That means in this complex number, the real part is 0. So in the real part 0 and in the imaginary axis 2I, 1I, 2I. So this is where I have my number. I'm going to circle it and rename it since I do not have enough space here to write down the whole number. And then 3 plus 2I. So in the real axis it's 3 and it's 2I. So if I extend these two lines, I have 3 plus 2I, which is the second number. And then I have the third number 1 plus 4I. So that is right here. I then have 4, where this is basically equal to 4 plus 0 into I. So in the real axis, this is 4 and in the imaginary it's 0. So this is where I'd have that number. And then I have 3I, which is 5, and I have -2, which is 6, and then I have -2 plus 3I, which is, if I extend this line, this line this way, and then plus 3i, which is I, 2i, 3i right here. That is the 7th number. And then last, as the 8th number, I have 4 minus 2i. So 4 minus 2i right here, which is 8. And finally I have minus 1 minus I, which is right here. Let's look at addition, subtraction, multiplication and division between two complex numbers. So as the question, let z1 be 2 plus I and z2 be 3 minus 2i. Both of these are complex numbers, and perform addition, subtraction, multiplication and division on z1 and z2. So to begin with, addition is quite simple. You simply add the two real parts together and two complex parts together. So let's say the resulting number is z, and z is z1 plus z2. Now I write down z1 2 plus I plus 3 minus 2i, which is z2, and then 2 plus 3 becomes 5 plus I plus minus 2i becomes minus I. So plus into minus becomes minus, so I minus 2i is minus I. Afterwards, let's look at subtraction between the two numbers. So let z be z1 minus z2. So if I write down z1, which is 2 plus I minus 3 minus 2i. Now 2 plus I, and then minus into positive becomes minus 3. Minus into minus becomes positive. So plus 2i. So again, I add the two real parts together. 2 plus minus 3 becomes minus 1. Plus I plus 2i becomes 3i. Now for multiplication, let's say z is equal to z1 into z2, and z1 is 2 plus I into z2, which is 3 minus 2i. So when doing the multiplication, I multiply this 2 with 3 and 2 with minus 2i, and then I with 3 and I with minus 2i. So basically it is much convenient for you to like divide this expression into 2 like so, and then multiply this portion and plus I into again z2, and then it's simply multiplication between these two numbers. 2 into 3 is 6 minus 2 into 2 is 4i plus I 3i plus into minus is minus, so minus 2i squared. Now this 2i becomes I squared is minus 1, so minus 2 into minus 1 becomes plus 2. So 6 minus 4i plus 3i minus 2. Now plus 6, this should be positive 2. 6 plus 2 becomes 8. Minus 4i plus 3i becomes minus I. So this is the resulting complex number from the multiplication between z1 and z2. Now we shall look at division. So let's say that the complex number z is a result of z1 being divided by z2. z1 is 2 plus I, z2 is 3 minus 2i. Now the goal here is that to convert the denominator into a real number. So the easiest way to do this is to make sure that I is to like convert I into a real number. So Before doing so, I would like to remind you that this expression x minus y into x plus y results in x squared minus y squared. So we can use that to actually make sure that the entire denominator becomes a real number. So to do that, I would multiply the entire expression, the numerator and the denominator, by 3 plus 2i. So what I have done is to convert the entire expression into this form. But it doesn't change the initial form. These two are still equal because these two expressions get cancelled by each other. So which results in 2 plus I into 3 becomes 6. 2 into 2i is 4i. 3 plus 3i plus 2i squared. In the denominator, 3 squared minus 2i squared. So if I simplify this, 3 squared is 9 and 2i squared is 4 into minus 1, and minus into minus becomes positive 4. So this part becomes 13. In the numerator, I have 6, but here I have, this should be 2i squared. I into 2i becomes 2i squared, so this becomes negative 2. So 6 minus 2 becomes 4. 4i plus 3i becomes 7i. In the denominator I have 13. So in order to get this to the previous to the complex number format, I can simply write 4 over 13 plus 7 over 13 into I. So this is the basic format of complex number being a plus bi, where a is 4 over 13 and b is 7 over 13. Let's use the concepts in complex numbers to find the roots of the equation 48 into x to the power of 4 plus 2y to the power of 6 equals 0. So before trying to solve the roots, I would like to reiterate the fact that there exists such a relationship such that x minus y into x plus y is equal to x squared minus y squared. So as you can see, if I can somehow get this equation to this form, I can easily get the roots such as x minus y into x plus y. So let's see how we can do that. Before doing so, I would like to break this entire expression into its squared of two components. So I can break this 48 into 16 into 3 into x to the power of 4 plus 2y to the power of 6. So this is because I can easily take 16 to be to the square of 4. So 4 root 3 x squared plus root 2 y cube. Now all I have to do is that to change this sign over here, and this expression would match the form of this expression. So again, you know that I is nothing but square root of minus 1. So if I take square root I squared, that becomes minus 1. So with that in our mind, I can say that positive plus sign is nothing but minus into minus. So I can say that minus into minus 1 into this expression so you can see that this expression and this expression is the same, since minus into minus 1 becomes plus, and I can say that minus 1 is equal to I squared. So Now you can see that if I get this I squared inside, it is basically the same expression as s squared x squared minus y squared. So to make it more clear, I'll write down like so: I root 2 y cube squared. So now I can get the roots of this equation same as in here. So I'll write down the roots as 4 root 3 x squared minus I root 2 y cube into 4 root 3 x squared plus I root 2 y cube. So if I take the I to this side as the form a equals a plus bi, this becomes so that way we have found the roots of this expression right here using the concept of complex numbers.